So please join me in welcoming Andy Yonelinas.
All right, well, thank you very much for that very kind introduction. I think the moral of the story is just surround yourself with very smart people and you'll do well. So keep that in mind for the graduate students and postdocs out there. You don't have to be smart, but if smartness is around you, it'll kind of ooze in, or it'll appear to ooze in. We've known for a long time that our ability to remember the important events of our lives is critically dependent on the medial temporal lobes. And my voice is coming in and out. Can you hear me? It's fine. Okay. It's odd here. And of course, you can't start a memory talk without having this image or something like this image on the screen. Of course, this was a very influential case of HM who had intractable epilepsy, and the surgeon removed the hippocampus, or the medial temporal lobes, bilaterally, and this led to a dense amnesia, meaning that he was unable to remember the important events of his life, despite the fact that other cognitive abilities like language and intelligence and perception, and even some forms of memory like short-term memory, so he could hold on to a telephone number just fine, those were intact, yet his ability to retrieve the episodes in his life had disappeared, essentially. Now, this has really kind of opened up the field of memory research and allowed us to try to kind of get into the circuitry of memory. And it led to a number of very influential models of memory. And I'm thinking about the systems models that were very dominant in the 80s and 90s, like Endel Tulving's episodic semantic distinction, or Larry Squire's declarative, non-declarative distinction. The idea being that the medial temporal lobes, these structures that were removed, unfortunately, in this patient, were critical for supporting a certain form of long-term memory, this declarative or episodic system. And that other forms of cognition and memory were supported by other cortical regions. Now, what have we learned since then? That's kind of where I want to start off with. And basically, what I'm going to talk about today are kind of some of the changes or advances that I think have been kind of important in terms of understanding the medial temporal lobes. And we'll be looking at the functions of different subregions within the hippocampus, and we'll be looking at, more specifically at what exactly the functions are that this system or multiple systems really support. And those ideas have really changed, I think, since the time of the declarative and episodic sort of systems approaches. Now, the players that I'm going to be talking about are illustrated on the top. Primarily, we'll be focusing a lot, of course, on the hippocampus in red, and the surrounding parahippocampal gyrus, the tissue immediately surrounding the hippocampus. I'll refer to the pararhinal cortex as the more anterior one-third to one-half of that structure, and the parahippocampal cortex as the more posterior section. Now, those two medial temporal lobe regions are really receiving a lot of visual input from the two classic visual streams, the ventral and dorsal stream. So the pararhinal cortex is receiving a lot of information from the what stream. It's telling you what objects are currently being perceived. The parahippocampal cortex, on the other hand, is receiving a lot of information from the dorsal or the where stream, so where in space things may occur. Okay, now that then is projected into the hippocampus. And of course, the amygdala is also playing a role, as everyone knows, with respect to emotional responses and potentially specifically fear responses. Okay, so these are the players that we're going to be looking at. And what I'm going to do today then is kind of walk through a couple of different areas of research. And the first will be looking more specifically at what do we mean when we say episodic memory is impaired, and looking at different types of episodic memory, specifically recollection versus familiarity, and how they play out with respect to these different substructures, which regions are important, and which types of episodic memory are disrupted in patients like patient HM. And from there, we're going to take a little bit of a detour and then start to look at some cognitive processes that, at least initially, were thought to be normal in these types of patients. But on further, more careful examination, it turns out these structures are also playing a role in some other cognitive abilities. And I'll talk about some visual short-term memory tasks and some perceptual tasks, and make an argument that we should be thinking about the function of the hippocampus with respect to its ability to support high-resolution binding. I'll try to unpack that idea as we go along. From there, I'll move on to some work on emotion, and basically make the argument that what we have to do is, when we're thinking about emotional memory, we have to think about something that's fundamentally different from the type of memory we're talking about in usual lab experiments that's supported by the hippocampus and these substructures. That in fact the amygdala may be supporting a separate type of memory, or maybe a separate system all into itself. And then from there, we'll talk a little bit about the effects of acute stress on these various different medial temporal lobe systems, and at least some of the beginnings of the studies that we're conducting to try and understand how these different systems are impacted by things like more chronic stress or acute stressors. Okay, so now, so going back to patient HM, when we say patient HM is amnesic, what do we mean by that? Okay, now, the literature on memory has been pretty clear for a long time that there are, in fact, two fundamentally different forms of episodic memory. In fact, this goes back to Aristotle, who distinguished between the ability to recollect, that is to kind of re-experience specific details about a prior event, okay, versus the ability to judge that an item was previously studied. It's familiar, even in the absence of recollection. Okay, so we know that these things are functionally distinct. There had been a growing literature from the electrophysiological literature for many, many years, just suggesting that these things were physiologically distinct forms of memory. And so you have to ask yourself, what's impaired in patients like HM? Do they have a selective impairment in recollection? Is it involving familiarity? Is it involving both? Maybe none of them. Okay? So it turns out that it depends on specifically what part of this medial temporal lobe system is involved in the lesion as to whether or not recollection and or familiarity will be impaired. As far as I know, recollection and familiarity were never directly measured in patient HM, so I can't actually answer the question about HM, but I can tell you a lot about patients that were very much like HM with respect to the type of lesion that he had. But before we get there, I'm going to take a bit of a sort of methodological side street for a moment and talk about how we measure these things. How do you measure recollection versus familiarity? There's a large debate about it. It depends upon who you ask as to which the correct answer is. Endel Tulving had some very strong opinions about this. He said, let's just ask the subject to introspect and tell us, yes, you recognize that item as being in the study list, but do you remember specific details? Or do you just know it was studied without any recollection? It's remember no procedure, all right? A procedure that made many of us uncomfortable because of its kind of reliance on introspection. And so others had developed more objective measures, such as associative versus item memory contrast. So you could say, if I want to measure recollection, I could ask you specifically, well, what was the detail about this study item that I'm interested in? Was it on the left side of the screen, the right side, or who was the speaker? When did it occur? So on and so forth. So I could objectively measure your recollective ability. Or I could just measure item familiarity. Have you seen this thing before? And dissociate across these different tasks. Okay. There's another method that we've been using quite a bit in the lab. And of course, if you ask me, I would say it's the method everyone should be using. And that's the receiver operating characteristic approach, and it's more of a sort of psychophysical approach. The procedure is relatively straightforward. You simply measure performance in a recognition test at different levels of response criterion or response bias, and you can do that many ways. You can just ask subjects to rate how confident they are about their memory decisions. And so what you can do then is you can plot performance, and so you plot, say, the hit rate on this axis on the left, that is the proportion of items that they correctly recognized, against their error rate or their false alarm rate, that is the proportion of non-studied items that they incorrectly recognized. And you just do that as a function of their confidence. So the leftmost point would be the high confidence items. The next point would be the high confidence items plus the next most confident items, so on and so forth, in a cumulative manner. So what you can see here is performance as a function of confidence. And you can look at the shape of the receiver operating characteristic and derive parameter estimates for recollection and familiarity. Now, I'm not going to test you on this, so you don't have to worry too much about the details. But the idea is you simply conduct a nonlinear regression, and you regress out the intercept and the curvilinear component, and you end up with these parameters that measure what we're claiming are recollection and familiarity. Okay? The idea, when it comes right down to it, is that when a subject recollects something about a specific event, I remember it was the first word in the list, and I made a sentence about it. Okay? They're going to be highly confident about those items. And in fact, that's what's going to drive the intercept. Okay? Whereas if they're just responding, I think I've seen that on the basis of familiarity, it'll produce a curvilinear curve. Okay? And so those are the two components we're pulling apart. Now, there's good reason to be very skeptical of any kind of modeling approach like this, that the parameters really map onto what we think they're mapping onto. And there's a pretty immense literature at this point suggesting that, in fact, they do. So you can run any experiment you like with any population you want and across any manipulation that's been done pretty much. And what you'll find is the three different methods tell you exactly the same thing. So it just gives us a little more confidence that whatever the method is, it converges with these other approaches. So we're pretty confident in these different methods. And in fact, we do tend to bias toward the receiver operating characteristic method for two kind of pragmatic reasons. Well, I'll just focus on one. One is that it allows you to very clearly differentiate between sensitivity, memory sensitivity, and response bias, which is a really important thing to do. Okay? It turns out that if you just measure overall performance, like a hit rate, single proportion correct, okay, very often you can't determine whether or not a difference you see in, say, between two patient populations or a control group is due to a difference in sensitivity or due to a difference in response criterion. Okay? Because performance can vary in terms of response criterion, and the shape of the function can differ quite dramatically. And I'll show you some examples of that a little bit later on. Okay? So that's one of the reasons we like to use this method. It provides you a way of really carefully separating memory sensitivity from biases that you may not be so interested in. Okay? And that will be important. Okay? But for pretty much everything I say today, it really doesn't matter which method you prefer. They all tend to lead to the same kinds of conclusions in terms of brain structures and the role of these types of memory. Okay, so those are the procedures that people have been using. Now, what about patient HM? Well, it turns out if you look at patients like HM who have pretty extensive medial temporal lobe damage, okay, that includes the hippocampus and the parietal cortex. That's that anterior cortical region surrounding the hippocampus. And remember, it was an anterior temporal lobe resection in that patient. What you tend to find is that the patients will have severe deficits in both their ability to recollect details and their ability to make familiarity-based judgments. And this is actually a bit of a surprise to us. And admittedly, when we first went into this, we were hoping to see a nice association between a selective recollection impairment and leaving familiarity intact. But that was not the case. Now, we've now seen this in many, many different types of patients. This one example is again, epileptic patients, but here with unilateral resections of the anterior temporal lobe. Okay, it's seen with lots and lots of different types of patients. However, if you find patients with selective hippocampal lesions, okay, and we've looked at many different types of patients like this, hypoxic patients, of sudden death patients. If you get them early enough, will have selective atrophy, sometimes within area CA1 within the hippocampus, leaving the surrounding cortex unaffected. What you find here are patients with these selective recollective impairments. So their familiarity-based judgments look completely normal. So selectively taking out the hippocampus selectively pulls out recollection. And in contrast, if you're lucky enough to find patients with damage to the surrounding parietal cortex that does not impinge upon the hippocampus, you get exactly the opposite. So these patients will have deficits in familiarity-based responding, yet they'll be able to tell you specific details of the recollected studied event. Okay, so you can essentially doubly dissociate these two processes with respect to these different brain structures. Admittedly, this was not something that I had expected to see when we initially went into this, but it's pretty clear now that you can doubly dissociate these, certainly with lesions. Okay, now, lesion patients in humans can always be criticized for many different reasons, hidden damage, so on and so forth, selecting specific type of subjects. So, of course, you always want to verify any of these kinds of results using some other methods. And these results have been nicely replicated in both animal studies and in human neuroimaging studies. And here's just one set of results. This is studies using ROC analysis in humans, and a study that Howard Eichenbaum conducted looking at rats where he selectively lesioned the hippocampus. And I was very interested to see how this experiment turned out, of course, because he's in the position where he has much more control over exact lesion location. And I remember the day that Howard sent me the first preliminary data, which turned out to be the final form of this experiment. And he said, I think you'll be happy to see what happens with rats with selective hippocampal lesions. And I pulled up the image, and it looked much like this, and I said, that's my data. And I emailed him back. I said, Howard, you sent me my data back to me. I'm sorry. I thought, he's getting a little older. He got a little confused. But in fact, it was the rat data, and it was exactly the same thing that we'd seen in humans. Okay, so it turns out that rats with selective hippocampal lesions also can't recollect. Yet their familiarity-based judgments seem to be normal. Now, if we could just get them to use a remember no judgment or task, we'd sell it, but I don't think that'll ever happen. Okay? But anyway, the ROC methods are nice because you can use it in different species. You can use confidence or ROC methods in small children and demented patients and all sorts of different groups that you probably wouldn't be tempted to use, say, subjective report procedures with. Okay. Now, so we've also seen this in lots of MRI studies, and this is just an early review from 2007. I think there were about 20 experiments published at this point using fMRI to look at recollection and familiarity. And this just shows you the number of studies that show activation in these different brain regions that are associated specifically with recollection or familiarity. And the main thing to look at, first of all, is the red bar on the left shows you the number of studies, the proportion of studies in which they were designed to isolate recollection that found hippocampal activation, quite a few, whereas the blue line shows the number of times the parietal cortex was related to recollection, very few. You see exactly the opposite when you go over to familiarity. For familiarity, the predominant effect is that you see a parietal involvement in familiarity-based responding, and you don't see a hippocampal involvement. So again, a double dissociation with respect to the involvement of these two regions that are sitting right next to one another with respect to recollection and familiarity. Okay. The one interesting thing that the fMRI data showed us, which we could not have guessed about because of our lesion studies, was the involvement of the parahippocampal cortex. We hadn't been able to find patients with those types of lesions, but what the imaging data suggests is that the parahippocampal cortex, that more posterior part of the medial temporal lobe, seems to be acting more like a recollective signal. It's more like the hippocampus than it is like the parietal cortex. And at first, we sort of ignored that, but it seemed to be pretty consistently observed across studies, and we now think that the reason the hippocampal cortex is involved in recollection is because it's involved in the retrieval of contextual information or spatial information. And when subjects remember a specific event, they're likely retrieving that contextual information. Okay. So these are the sorts of results that have led many of us to kind of what I'll call a modal model. It's sort of the model that's bubbling out of a lot of labs. We tend to refer to it as the BIC model, or the binding of items and context model. And the idea is pretty simple, and it basically says that what the hippocampus is there for is binding together the different bits of information that are important in making up this event. Okay? And two very important chunks of that event are going to be the item information, the objects, the people, the things that occurred in that event that it receives from the parietal cortex, with the contextual information that it's receiving from the parahippocampal cortex, so the where, for example, information. And the idea then is to retrieve that recollected event. One would need to use the hippocampus to retrieve that binding and produce the appropriate recollected information. So the idea, though, is that the parietal cortex, in the sense that it's involved in identifying object information or item information, should be sufficient to make judgments about whether that item is familiar or not. Okay? Whereas the hippocampus is going to be necessary if you're going to be having a full recollected experience. Okay? So that's basically the model that was designed primarily to kind of account for the episodic memory results that were seen in the animal literature and the human literature and the fMRI results. But what's interesting, I think, about this kind of way of thinking about memory is that it's not saying that the medial temporal lobes is a memory system, per se. It's saying, look, the different components of the medial temporal lobes are doing different things. Okay, the hippocampus is binding things together, and the parietal cortex is taking care of identifying what the objects are, and the parahippocampal cortex is taking care of seeing information. Okay? There's nothing necessarily linked here to long-term memory. Now, of course, having a binding that links the object to a specific location could be very useful if you're in an episodic memory test. But it should be useful in other tasks as well, as long as that type of representation could be helpful in completing the task that the experimenter gives you. Okay? So it led us to think that the hippocampus and the medial temporal lobes as a system might not be a memory system per se, but that it might be supportive of any kind of cognitive task that requires these types of representations. Okay? Now, about the same time, a lot of very interesting work was coming out of the UK, and I want to give a little plug for the work from Andy Lee and his colleagues. And this paper I remember specifically coming out, and for years I did my best to ignore it because I could not make any sense out of it. But basically, it was a study of amnesia that had no memory measure at all. It was all just perception. It was this odd man out paradigm. And so the idea is which of these items is different, and they stay on the screen for as long as you want. And what they found is that selective hippocampal patients, which is the group that we were most interested in, were unimpaired at the simple item recognition judgments, or the item perception judgments, but they were impaired if the task involves some kind of spatial representation, like this 3D rendered scene at the bottom. I don't know if you can see that from where you are, but the idea is that even in a perception experiment where there was no delay, without a hippocampus, you really can't do that task. And it suggested that the hippocampus was playing a role potentially in perception. Okay? At the same time, work from the Olson lab had suggested that in working memory tasks, short-term memory tasks that were supposed to be preserved in hippocampal patients, that if you looked at patients with hippocampal lesions, that they, in fact, were impaired. So in this case, the subject has to remember, say, a small number of colored squares. And then at time of test, they're cued and asked, was this the same color as what it was just a second ago, or 2 seconds ago, or 4 seconds ago? And what they found was that hippocampal patients were significantly impaired in this working memory task. Again, hard to make sense of given the kind of systems approach that a lot of this work originated arguing for. Okay? However, it turns out this work is very, very controversial, and there have been many huge debates, like nasty kind of punching out debates at conferences about whether or not the hippocampus really is important for perception and working memory or not. Because some labs run very similar experiments and find that the hippocampus plays no role whatsoever, so the patients are completely normal. Okay? And this debate had been going on for a number of years. And when we thought to start looking at this work more seriously, we looked at the literature and we found that there were two things that worried us about the existing literature that might be related to the mixed results. And the first one was this sort of methodological issue, which I suggested earlier, which is that most of these studies relied on single parameter measures of perceptual sensitivity, like percent correct, yes, no, did they get 80%, 90%, or whatnot. Now, we know from the memory literature that that's a big mistake. You should always look at the entire receiver operating characteristics so you can really pull apart sensitivity and biases. And that's almost never done, at least at this point in the literature. So that's one of our concerns. The second one was that what we found when we looked at this literature is that it seemed as if in many of the cases where they were impaired, the tasks required the patients to retrieve or make use of very high-resolution complex bindings. Okay, just as one illustration, in this working memory paradigm, it's in black and white, and I apologize for that. It was actually in color. But they used very vivid and different types of colors throughout the experiment. Okay, and the patients were impaired. In contrast, in the Jennison study in 2012, they used canonical colors, and they only used, I think, 4 or 5 or 6 of them: black, white, they're not even colors, black, white, red, green, blue, maybe one other color. Okay? So when the colors that the subject has to hold on to are canonical colors, and they never change across the experiment, okay, you don't seem to need the hippocampus. But when the patients are required to retrieve, was it this specific color or not, then it seemed as if they were showing impairments. And now this is just looking across experiments, so we have no solid basis at this point to say that, but those are the 2 intuitions we had when we went into this. And those are the 2 questions we really tried to answer. So a whole series of experiments were conducted. I'm going to talk about this one first. It's a perception experiment. I kind of like the results, and it's really got the study that got us started. Miriam Alley was a graduate student at the time, and she really spearheaded all of this work. So basically what she did is she wanted to look at a simplified version of the scene perception paradigm to see if the patients were really impaired. And she wanted to, first of all, get rid of the potential confound, which is that you don't want too many scenes on the screen because that might become kind of a long-term memory test, and people might compare one to the other and go to the next and so on and so forth. So she just had 2 scenes appear on the screen, and they were either identical or one had been manipulated in a subtle way. So she had pinched the scene in or expanded the scene out a little bit. I don't know if you can see that on the top. Are those the same or different? Can you make those out? Maybe you're all amnestic. I don't know. They're actually slightly different. This is somewhat unfair. As a subject that takes up the entire screen, boom, these things appear, and you make these decisions. It's not easy. And we titrate this to be a very difficult test. But the question is, does an amnesic patient who doesn't have a hippocampus have a perceptual deficit on this type of a task? Now, what she did is her manipulations were not of individual features, but of the kind of the relational structure of the whole image. It was pinched in very subtly or expanded very subtly. Okay? And what she did is had subjects in this case just rate the confidence of their perceptual judgment. You can see where this is going with respect to doing some ROC analysis. And she plotted performance as a function of whether they were in the patient group or the controls. She actually ran hippocampal patients, medial temporal lobe patients with larger lesions, and controls. Turns out the hippocampal and medial temporal lobe patients performed similarly, so I'm collapsing the data here. But as you can see, performance is much lower in the patient group. The red line is lower than the blue line, okay? Meaning there's a sensitivity drop in amnesia, and it's not a response bias drop, okay? Now what's interesting is if you were to have conducted an experiment where you just collected a single response, proportion correct, okay? And the subjects happened to pick a strict response criterion, say the point at the very left, you'd say they weren't impaired. The patients looked normal. Okay? It's only when you include the more low confidence responses that you see that they're impaired. Okay? The way we've described this is essentially what you find in these types of perceptual judgment tasks are 2 different types of responses. One we call perceiving, and those are trials where a subject looks at the 2 pictures and they go, oh yeah, that's definitely different. The window is angled on this one and it's not angled on that one. They can tell you qualitative information about that makes the 2 scenes different. Okay? They tend to be very high confident responses. On the other hand, there are many other responses where you just go, oh man, I don't know. It seems like something was different, but I can't tell you what it was. Those are what we call sensing responses. They tend to be low confident responses. And that's what it turns out patients have problems with. Okay? So they have problems with sensing, in this case, the curvilinearity function, and they don't have problems with the high confident perceiving responses. So they're as likely as you and I are to make correct judgments about, yes, that specific thing changed, and I can tell you what it was. Okay? But when they're making sensing-based judgments, they're not nearly as accurate as you and I are. So even though we're guessing, or we're kind of guessing, we're doing pretty well. But you don't do pretty well if you're an amnestic patient. You have a hippocampal lesion. Okay? So this is a distinction which was kind of surprising to us. But in general, what we see are impairments in perceiving and not in sensing and not perceiving responses. And these are just the parameter estimates that come out of doing an ROC analysis. And that will reoccur again and again, as we'll see. Now, Miriam also conducted an fMRI experiment in normal control subjects. She wanted to verify that, in fact, in controls, the hippocampus was also involved in this perceptual task, and in fact it was. And this just shows you hippocampal activation as a function of confidence, and you see it ramps up. And so even in healthy subjects, it appears that the hippocampus is engaged when you're making these types of perceptual judgments. Okay? And again, it tends to kind of ramp up with these low-level confidence responses. So it tells us that the hippocampus is necessary for scene perception, even when there's only 2 scenes on the screen for a very brief time. Okay? And it tends to show up in these low-confidence, what we call sensing responses, not in the high-confidence scene changes. So that's what first kind of got us moving on the perceptual kind of set of studies. We've then looked at this using various other different methods. One potential concern is there might be something special about scenes in the hippocampus. There are a number of theorists who have argued that the hippocampus is designed for spatial representations, and it should be particularly involved in those tasks. But we tend to find that it generalizes to lots and lots of different materials. Our first attack at that was looking at these funny objects here, and the change, and it's a perceptual change judgment. Are they the same or different? And the changes can be either global or discrete. So in the global one, you probably even can't see that from out there, but the body has been slightly twisted. And in the discrete changes, the little leg things on the outside have been swapped out. So it's a discrete change versus this global change of the overall configuration. And it turns out that the patients, again, are critically impaired on the global change. They're not impaired at making those discrete change judgments. And again, the parameter estimates tell us that they're showing an impairment in these low confidence sensing responses. Okay? So we see that with scenes, we see that with these objects. We've then moved to even simpler stimuli, so visual short-term memory change detection paradigms. So in this specific experiment, subjects are looking at either a high-resolution short-term memory task or a high-complexity task. We're balancing for overall difficulty in this setup. And in the first case, they have to remember these 3 objects. There's a 1-second delay, and then they're presented with an intact or a changed probe trial. And in this case, I don't know if you can tell, but the purplish thing has changed a little bit. Okay, so you should say that's a change trial instead of a same trial. In the bottom one, it's high complexity, meaning there's more items to hold on to, but the change is going to be more a simpler change, so it's a more dramatic low-resolution change. And in this case, the purple changes to a yellow. Okay, so we're trying to drive the hippocampus by either making the task, the working memory task, high resolution or high complexity, relatively one another. And again, basically what she finds is that hippocampal patients are impaired, and they're impaired again on both of these things. So if you make the working memory task either require high resolution or high complexity, you have a hippocampal involvement and hippocampal impairment. And again, the impairments tend to be in the sensing-based responses, these low-confidence responses, which they don't have. They can hold on to the high-confidence trials in a manner that's similar to what we see with control subjects. Okay. We wanted to move away from the ROCs just because sometimes it's good to use other people's inferior procedures. So we used the forced choice procedure, and this is actually a procedure I like an awful lot. What it allowed us to do was ask if we looked at high precision memory in a short-term memory paradigm for different types of information, we could do that at time of test by simply varying how difficult the test lure was or how different the test lure was from the target item. So for example, in the top center, subjects are trying to remember the locations of 3 objects. Okay, they appear on the screen for a very brief time, and then at time of test, they're given a 2 alternative force choice test, either for object location that's either high resolution because the lure is very close, or it's low resolution because the lure is moved farther away. Okay? Similarly, we can test memory for color. So you get 3 objects, and you have to remember the precise color. We can test you using a similar greenish lure or a very dissimilar red lure. Okay, and we're looking to see if they have impairments specifically related to the precision requirement. Now, what we did in this experiment is, importantly, the high precision and low precision were matched for overall difficulty. So we increased the set size of the low precision task. So it's equally difficult. If we find a difference in performance, it has to do with precision, not difficulty per se. Okay? And importantly, what we found is that the patients were completely unimpaired at the low resolution working memory discrimination. Okay? So in location on the left, you see the low resolution. The blue bars are the controls. The red bars are the patients. They are unimpaired. If you go to the high resolution condition for the location, they're significantly impaired. If you go to the color paradigm, there, the low resolution paradigm, they're completely unimpaired. It's only when you require high resolution binding that they become impaired. Okay? And again, we've matched for overall difficulty in these tasks. So it's not just that you make the task more difficult and they have a problem. It's the precision that's particularly important here. Okay? So this led us to be fairly confident that there is something really fundamentally important about the precision of the representation, not just the amount of stuff you have to bind together or the difficulty of the binding. It's the getting that precise color or location information. And we're now looking at what other dimensions might also be important in supporting these types of hippocampal responses. Okay. Now, along this line of looking at different dimensions, Arne Ekstrom is a colleague in my department, and he's very interested in navigation, and he could not believe that I'd gone through my entire career without doing a single navigation study, and it was his duty, he felt, to make sure that I conducted one. So kicking and screaming, I said, okay, fine, we'll do it. Why don't we try some of this high-resolution stuff and see if it helps understand what's going on in amnesia and navigation. And one of the things that Arne had been very worried about was that if you look at the animal work on navigation, the story is very clear-cut. That is, you take out the hippocampus and rats can't navigate. Right? They can't get to the water maze location they were supposed to be getting to. But humans, it's somewhat of a mixed story. Some amnesic patients have profound navigation problems, and other patients did not seem to have impairments. And sometimes they're unimpaired in these navigation tasks. Why would that be? Well, what Arne suggested is maybe we could generalize our results from lab into this more realistic sort of situation. And maybe what's going on is that what the hippocampus is there for is not navigation in general. Maybe the cortex can get you in the general area that you want to get to. But what the hippocampus is for high precision memory, getting you exactly to a specific location that you need to get to. And so basically we took a paradigm that he'd been working with. It's basically the water maze with virtual reality goggles. And the patients come in and they are presented with a scene. You can see sort of in the center there's some paintings on the wall and some doors and a couple of sparse environmental cues. And an object would then appear at some location in that room. Okay? Then we take them out of the room, sort of, wait a couple of minutes, put them back in the room, and then have them walk back to the location where that object was seen. And when they were confident they were there, they'd sort of click on this response thing. This is where that object was. Okay? So it's like the water maze. Now, basically, what we found in that study is that if you just scored this in terms of very gross coordinates, like it was in which of the 4 coordinates in the room was the object in, the patients were completely normal. Okay? They could tell you, yeah, there was an apple sort of over here. Okay? But if we scored exactly where they were and only counted like as a hit a trial which they got exactly to the right location, or within a foot, or within a yard, or within 4 yards, okay, that's when we saw the impairments. Okay, so what this graph off to the right shows is that the patient is actually significantly better than the controls at getting the right quadrant. This is just one patient in this initial study. In general, they're just normal, but this patient did particularly well. But if you score it with using very narrow scoring windows, so you got to get exactly to the right location, they are massively impaired. Okay? So what hippocampal damage does, it doesn't mess with your ability to navigate in the general sense of getting to the basic right location. The cortex seems to be able to do that for you. And what the hippocampus allows you to do is to get to more precise information about exactly where that object was or where you want to be. So we think that the precision idea is a pretty useful one in trying to understand the involvement of the hippocampus in many different paradigms. And so the story then is not much different from what I proposed earlier with respect to these three main players. But basically what we're adding to this is that the hippocampus binds together the different aspects of an event, i.e. the items and the context, to form a complex, high-resolution representation, which can impact long-term memory, short-term memory, perception, maybe future thought. There's many different things that it may be playing a role in. And we think this way of thinking about the hippocampal function is potentially useful in understanding the involvement of these medial temporal lobe regions in various other paradigms as well. Okay, so far I've been talking an awful lot about really boring memory materials, okay, word lists, okay, pictures of objects or these weird colored things. Most of what we care about, though, when we think about day-to-day memories are the important events in our lives, the things that are emotional, okay? Does any of this tell us anything about any of the good stuff? And it's a very good question. It's not totally clear, okay? So we're, of course, interested in emotion because emotional memories tend to be very vivid. And if you ask most people on the street, what are the most memorable things in your life, they will list off, they got married, they got dumped, whatever nasty things may have happened to them in their lives, okay? The emotional things really stick around. And in fact, that's very well documented in the lab. Okay, so we know that emotional memories are particularly resistant to forgetting. And now that could be for various reasons. For the obvious one is that emotional items can attract more attention and elaborative encoding than neutral items, which would lead to better encoding of that event and better memory for that event. Okay, so just as an example, a year from now, you'll remember nothing of what I've said. I'm pretty confident about that. Okay? But you may remember this poor fellow with a snake on his face. Okay? Although maybe in Australia it's less of a salient thing. I don't know. But certainly in Canada, this freaks everybody out. Okay? But there's more to emotion than simple salience and significance and better encoding. Because it turns out that these emotion effects tend to emerge over time. Okay? So very often what you'll find is that after studying these two pictures, if they're balanced for complexity, which these two aren't, but if I test you, say, within 20 minutes or so, you would have equally vivid memories for both of these events, and your memory would be approximately equal. Okay? However, if I test you over a delay, what we'd find is the neutral information gets lost pretty quickly, the emotional stuff sticks around. Okay? So it's not just better encoding. There's something that happens to these memories after the encoding event is over that preferentially preserves the emotional item. And what we were interested in is what was that? Okay? And how does that interplay with those medial temporal lobe systems that we've talked about so far? Okay? Now, everyone is at this point obviously going, well, Andy, that's a dumb question. It's obviously the amygdala is playing a role, but exactly what is the amygdala doing? Okay? Now, it turns out that there are really two ways of thinking about this in the literature. One really dominant way, and then the not-so-dominant way that I think is actually right. Okay? The dominant approach in this literature is to argue that for something that's been called the emotional consolidation model. And the idea here is that what the amygdala does is that it signals to the hippocampus that something important just happened. That was a really emotional event. Remember that thing, Andy, because you don't want that to happen again. She dumped you. Don't ever go out with anyone that looked like her ever again. Okay? And so the idea is that it's preferentially consolidating those emotional events. So the amygdala isn't forming the memory per se, but it's saying to the hippocampus, hey, you, remember that. Okay? And don't forget that binding that you created. So whatever the hippocampus was doing, binding the item and object stuff together, that should be benefited by emotion. Okay? So it should be a very general effect on memory. Okay? The second interesting thing about that consolidation idea is that what it predicts is that if the amygdala is modulating the hippocampus to create the memory advantage for emotion, lesions to the amygdala should wipe out the effect, okay, or diminish it. And similarly, lesions to the hippocampus should diminish that effect because it's operating on the hippocampus. Okay? So lesions to either of these important structures should be detrimental to this emotion advantage that emerges. Okay? There's another way that we've been thinking about this, however, over the years, and that is that the amygdala is actually serving as a type of secondary memory system of a sort that's specialized for emotional information. Okay? It's not just modulating what the hippocampus does, it's storing a certain type of memory representation, and that representation we think of as an item emotion binding. So the idea is that what we think of when something occurs that's very emotionally salient or fearful is the amygdala is actually linking that emotional response to the physical features of that specific object, such that there's now a link, an association formed between that stimuli and, say, a fear response. Okay? And the representation is actually supported by the amygdala itself, not by the hippocampus. So the notion is that for neutral materials, you have to rely on the hippocampus, linking item and contextual information. For emotional stimuli, of course, you can rely on the hippocampus to link that stuff. But in addition, you've got this separate system that's supporting a relationship between the item and the emotion. So if you get the two systems working, you're going to get slower forgetting than if you have one system working. Okay? And in addition, there's some good reason to think that the hippocampus might be losing information more rapidly than the amygdala. I'm not going to get into the neuroanatomy of that, but there's some evidence that's consistent with that. Okay? So the idea, though, is that both of these accounts can explain why we're so good at remembering emotional events. One is because we consolidate them particularly well, and the other is that we just have a separate system that supports memory for those, and that's going to lead to slower forgetting. Okay? So what are the results that lead us to prefer the emotional binding model? To do that, I'm just going to walk through one illustrative study, which is certainly not the best study out there, but it's nice in that it illustrates a couple of the characteristics that I think have been very well documented in the literature over the years. And in this type of paradigm, basically, subjects come in and we show them a list of items. So they include negative, nasty images like the man with the snake. We show them neutral images. It's a mix of these things. For half of the items, they're conducting a color rating task. For half of them, they're conducting a complexity rating task. That's what we're going to call our encoding context. So you encode it within a certain context. Okay, that'll make more sense in a second. On day 2, they come back in and they study a second list of neutral and negative images. Okay, and again, they do color rating for half of them and complexity rating for the other half. Okay, and then immediately after 5 minutes, we give them a memory test. And we're going to test memory for the items that just had occurred. Those will be the short delay items. And for items that occurred 24 hours earlier. Those are the long delay items. Okay, so we can see, does the emotion effect emerge over time? Okay. And then we're going to test recognition memory. We'll use Endel-Tulving's Remember No New procedure. We've used various different methods over the years to measure recollection and familiarity. Okay? But we're also going to measure your ability to remember the study context. That is, did you make a color judgment task about the encoding condition or complexity judgment task? Okay? So basically, what we see with this type of a task, if you look at overall recognition, for the 5-minute delay retention interval, there's no memory advantage for the emotional over the neutral. However, if you wait 24 hours, the effect emerges. Okay? So you see a lot of forgetting for neutral items. You see very little forgetting for emotional items. Pretty standard effect that's been seen many, many times. Now, if you break it down and you look at the recognition responses, are they remember responses or familiarity-based responses? What you find is the effect is captured entirely by the remember responses. So the boost in memory you see is a difference with respect to remembered responses. So you remember the nasty images and you recollect specific details about those images. It's not familiarity-based responding. Okay? But interestingly, this is one case, that was the first case where our source test or our second measure of recollection did something different from our first measure. And in this case, what we find is that the source judgment, so making judgment about what the context was that you encoded it in, did not benefit from emotion. Okay? So what emotion does is increases your memory for the item and the emotional characteristics of that item. It does not increase memory for the context that you encoded that thing in, okay? The type of processing that you conducted on that item, okay? And that has now actually been seen in many other paradigms. So The takeaway from this isn't the specific experiment, but in general, three things you almost always see now. Emotion advantage in memory, they're time dependent, they increase over time. Okay? Lots of examples. When it impacts memory, it impacts recollection, not familiarity. Okay? Measured lots and lots of different ways. But interestingly, it's limited to item recollection. It's the recollection of the specific characteristics of the item, not to the context, like the spatial context or the processing context as in that prior experiment. Okay? So it's not a general benefit in recollective memory, as one might expect from a consolidation approach. It's really selective to item emotion links, okay, which is what the emotional binding account predicted. Okay. Now, the interesting difference has to do with the neuroanatomy of these effects. That is, are the effects dependent upon the hippocampus being modulated by the amygdala, and so are both